Hello, everyone. It's my great pleasure to welcome today Makdesi with us for our online seminar presentation on interval methods in control engineering. And Anas is currently a postdoctoral researcher at the Ludwig-Maximilians Universität in München in Germany. And before that, he received his Bachelor of Science degree from the Higher Institute of Applied Sciences and Technology in Damascus. Afterwards, he moved to France for his master's studies and also for his PhD. And yeah, he did both of them at the Université de Paris-Saclay in France and completed his PhD in 2023. And yeah, his current research interests focus on data-driven controls, cyber-physical systems, monotone systems, and safety-critical system abstraction, and especially the point of monotone systems with corresponding foundations for efficient interval methods in control will now be the focus of his presentation. Anas, the floor is yours.
Thanks. Thank you for the introduction. I will dive into it immediately. So let's start. Yep. So I don't think I need to motivate the use of interval methods for an interval method seminar. I just want to say briefly that I'm interested in safety and safety critical systems in general, and more precisely, I also work on establishing safety for data-driven methods. And that's why interval methods are a great tool that helps with establishing safety. It helps with reachability analysis and with the worst case robust control, but it suffers some disadvantage, namely the conservatism or the complexity of computation for several in some cases. But we can alleviate that with the assumption of monotonicity. So monotonicity preserves the partial order. So what does that mean? Given two states, we have x1 is smaller than x2 component-wise, then I will know that the function of x1 will be smaller than the function of x2 component-wise. This will help us establish or calculate tight intervals for a given set. So the image of the interval here can be calculated by only studying 2 points, the corners of the intervals, and then we can establish the image of the set. And this result I will be using throughout this talk to say how we can use it in different settings. I'm gonna start with a small problem where we establish data-driven over approximation models. Then I will say how to generalize these models, how to compute safety controllers out of those models, and then use it using MPC, using the safe controllers. And then I will talk briefly about some of the new work we are doing recently about monotone embeddings. So let's start. And I will start with a simple example. So given we have a monotone function, we don't know the function, it's unknown, but we sample a set of data out of this monotone function. And then there could be plenty of functions that fit the data. In some cases, it could be an infinite number of functions. And as you can see, we don't assume that the function should be smooth. But due to monotonicity, I can say, in this case, let's say our x star here is smaller than x1 and larger than x1 and smaller than x2, then its image f of x star is smaller than f of x2 and larger than f of x1. So the image should be in the interval between fx1 and fx2. I can say the same for all the points between x1 and x2. And if I apply the same idea for all the points in the domain, I will end up with an interval valued map here in red, and this interval valued map will contain any function capable of generating the data. Moreover, this interval valued over approximation is optimal in the sense that any other map that contains all the functions capable of generating the data should include this interval valued over approximation. So it offers the least conservative estimate of the successor. And even in a more general setting where we have a multivariable case with bounded disturbance, I can apply a similar argument. So here, let's consider all the points in the yellow region. For any points here, we can say that x star is smaller than x6 and x7. With accounting for disturbance, I can intersect the region underneath y7 and y6 to give an upper bound on the successor of x star, and the same when it comes to x1 and x2. I have x star is larger than x1, larger than x2, then successor should be larger than y2, y1, y is also accounting for disturbance. I do all the intersection of all those sets, and I will end up with an interval valued over approximation for the region n star, for any points in the region n star, in yellow. And I can do the same for all the sets in this partition. This partition of the space is built using the components of the dataset. But this calculation could be costly because the cell in the partition will grow polynomially with the number of dataset and exponentially with the number of dimensions. So we can have a different setting where we fix the partitions a priori and apply the same idea, the same arguments. Here, for all the points in yellow, we can see the points larger than the set in yellow. Here we have x7, and all the points smaller than the region in yellow. Here we have x1, intersect the region beneath and above those 2 points to end up with an interval valued over approximation. This interval valued over approximation will add more conservatism, but it will be efficient to calculate. And so in a previous work, we established that the last interval valued over approximation we discussed offer the minimal interval valued over approximation on a given fixed a priori partition of the space. And we also found a way to calculate this over approximation efficiently. So with a complexity of n log m plus m, where n is the number of datasets and m the number of cells in the partition. And if we use the partition which is aligned with the data components, as we did in the first steps, we can say that this interval valued map or interval valued over approximation is the minimal set valued over approximation, as we said earlier. And we can generalize this case for maps of function written as the sum of a known nonlinear map plus an unknown monotone part. Till now, I talked about how to find over approximation of monotone system or monotone maps, and didn't talk about monotonicity and how widespread it is in real life scenarios. And it is. There are plenty of systems which are monotone in biology, in networks, and so on. But moreover, we can have some methods to transform a general type of system to work with using a monotone transformation to work in a monotone setting. And let's discuss this. So let's say, given a function f, which we know that its derivative is bounded between alpha and beta, then these two auxiliary functions, h and g, are monotone by construction. So basically what we can do is take the data set we have and then apply some transformation on it. So here the transformation to in the end we will get two data sets such as if they are generated from a monotone function, and work with those two data sets, apply the same methods we discussed earlier, and find an over approximation. And in the end, we will have two interval valid over approximation. From those two interval valid over approximation, we can reach a set valid over approximation that is guaranteed to contain the actual system. If we want to transform it to an interval valued case, we can apply some more calculation and end up with the interval valued over approximation. And you see here on the figure, you see the function in solid. We sampled some points from the function, applied our over approximation method, and ended up with this piecewise interval valued over approximation of the unknown system. But how we can use this over approximation in a safety setting to synthesize a controller? So let's say we have a monotone system now. So we have a state and input. F is unknown, the disturbance is bounded, and we sample a set of transitions. Here we have x, u, and the next step. Then we can apply the same over approximation method we already introduced and calculate the over approximation of a given cell. So here I'm partitioning the space of the states and inputs. The next step, I will give for each state for each cell in the partition of that state the symbol Q, and for each cell in the partitioning of the inputs, I will give them the symbol P. And now I can say that all the states in Q2, for example, under an input from P2 will transition to one of the two states, Q1 or Q2, under this P2 input. And this means that I can build a finite state representation, I call it an abstraction, that it's equivalent to this over approximation. And this theorem here is saying that there's an alternating simulation between the over approximation we established, we built, and the concrete system. And what's an alternating simulation? It's a fancy tool to say that I can work with the over approximation, find the controller for the over approximation, and then transfer it through an interface to control the original system. Moreover, there's an alternating bisimulation between the over approximation and the finite state representation. Bisimulation, the same as alternating simulation, but with more with asking more of the relation, because it needs to go both ways. So there's no loss of generality with working with either of these two representation or these two models. And then basically my finite state representation could be a model of the concrete original system, which is unknown. I can work with this abstraction finite state abstraction to find a safety control. And how we could do that? Uh, the idea is we can, with finite state models, we can make use of formal methods, algorithmic way to ensure safety. So here we can, for safety, for example, we can apply an iterative procedure to remove all the unsafe action. Let's say that Q1 is unsafe. I will start by removing all the actions that will lead me to Q1 and then remove all the states that don't have that have only unsafe actions and so on until I will end up with only the set of safe states and safe inputs or safe actions. But those safe actions aggregate a set of inputs that could be applied, or an interval of the inputs that could be applied to the concrete system. So how to choose one input out of this interval, and what if we want to optimize for some requirements other than safety? And here MPC comes for the rescue, and the idea will be as follows. So we want safety to be applied or respected robustly. So our state should be inside a given set. And then we will have a cost function to be minimized to enforce some performance requirement. And this will be applied through uh, MPC, and then our solution goes as follows. We will build two models of the system. The first is the set valued or interval valued over approximation that we discussed earlier, and this over approximation is guaranteed to contain the original unknown system. This model is used to find the set of safe controllers. Then we build a single valued estimation of the true function with one constraint, that this estimation, single value estimation, should be included in our set valued over approximation, which we call the compatibility constraint. And if we have this, then we have the following result. We can use the single valued estimation in calculating the horizon of our MPC, and if we add the constraint, the input that we apply to the system should be chosen from the set of safe inputs we calculated using the over approximation, then the closed loop system will always be safe and the optimization program is always going to be feasible. And this works for any estimation, single valued estimation, as long as it respects the compatibility condition. So it could be a neural network, and I don't know what, as long as it's contained in our over approximation, this theorem holds. But for the example that I'm gonna show later, we used a class of functions which are multi-affine, and they have some uh, nice things about them that makes working with them easy when we have an interval valued over approximation. And this is because the domain of the function is if the domain of the function is an interval, then the function can be written as a linear combination of the value of the function on the vertices. So any point of the system can be a linear combination of all the points on the vertices. Moreover, the value of the function is bounded by those values on the vertices, and it makes it a really nice candidate for an estimation that should be fit into an interval guided over approximation. We use a piecewise multi-affine function to estimate the unknown function. I'm not gonna go into details on how to do that, but for I will only show a path planning example. So here we have the model of a bicycle model, and our objective is to learn the dynamics of the vehicle using the set of data and then drive the vehicle to a given target while avoiding the obstacles. We sampled 1 million data transition. We partitioned the interval into 30 sections, and for the x and y, we have partitioned into 100 section and 400 section each. And then we build the over approximation. Then here you can see the over approximation of all the states. The original concrete, which is unknown, but we used to sample the data points in solid, and then the interval, the piecewise interval of our approximation, calculated using the method we discussed. From this, it was transformed to a finite state model, and this finite state model was used to find the maximal control invariant, and that will enable us to stay safe and avoiding the obstacle. Then we found the single value estimation using the piecewise of multi-affine function described earlier. And here you can see the error between the concrete original system and our estimation. And build an MPC type controller with the cost function only relying on the distance, because we know that there's no need to account for the obstacles, because the safety controller will do its works and will only gonna choose the input that will keep us safe. And so with this cost function, we were able to drive the car from the initial point to the goal. Finally, I want to talk briefly about some of the works we're doing right now, and it's just to give an idea of what we can do with monotone system or monotone function. So let's consider the following setup. We have a linear system where we have also a disturbance which is bounded. Then I can build a higher dimension, to be exact, a 2n higher dimension out of this linear system, and this higher dimensional system, I'm gonna call it abstraction or embedding, is monotone. And moreover, we have that this higher dimensional embedding alternatingly simulate the original system. So the same tool we discussed earlier, I can work with the embedding, find a controller here, and then through an interface, apply it to the original system to satisfy several requirements. But why go into a higher dimension? Well, for several of reasons, but I'm interested here in discussing one, which is it happens to be under some mild assumptions that the states of the embeddings act as an interval that bounds the state of the concrete or original system. And so if we calculated the trajectories of the abstraction, but sorry, if we calculated the trajectories of the embeddings, we are calculating the intervals that bound the trajectory of the concrete system or the original system. I don't want to go into details, but I just want to briefly show an example where we have a system where we apply three methods: interval analysis, Cora, and our monotone embedding to find to calculate the reachability and see that using this method of going to a higher embedding, calculate the interval, and for several time steps in the future, we will stay bounded while the interval analysis will fail, and it's gonna be comparable to Cora. This example was tailored for this seminar, so take everything here with a grain of salt. But there's some one claim that will stick, which is we will do the calculation with way far lower cost than Cora, for example, because in the end we're calculating the trajectories of the abstraction, and this is not affected by the dimension or the horizon length as much as it's the case with Cora. Finally, also briefly, just a teaser that I'm gonna say that this idea of embedding can be also applied in data-driven settings. So consider we have a function with bounded derivatives, and consider we're sampling, let's say, 2 points from this function, and the intersection of the growth cones built out of those two data sets will give us this overline G, underline G, and we can think of them as data sampled from a monotone embedding in a higher dimension. We established that this embedding is monotone, and to see why, let's take another example. Here you see that the points move to the left, and then G1 is decreasing, so not G1, overline G is decreasing, underline G is increasing. So there's an intuition of why they respect some order, which is the southeast order, and it could be transferred to the component-wise monotone order we defined at the beginning easily by just flipping some axes, and then we'll end up with a monotone embedding, or a dataset generated from a monotone embedding. Why would this be interesting? Because monotonicity offers a really nice tool to calculate invariance. So for a simple example, let's have this transition here. We have the point x and the transition x prime. So for all the points in green, I know only from this one transition that for all those points are smaller than x, then their next step will be smaller than x prime. And so no point will go outside of this green region. And we have an invariance, forward invariance of this region. And also in the general case, with up to n, where n the number of dimension, we can establish safety or invariance. Sorry, because let's say all the points in light green are smaller than x2 and x1, then they are smaller than their transition. So the transition of all the points in light green are smaller than the transition of x1 and x2. So they're smaller than the intersection of the area beneath x1 and beneath x2 prime. And so all the points in greens will transition to a point in solid green. And so the area underneath T also is an invariant set. And so we can use this idea to establish we can use it to establish safety, but we can use it to establish invariance of the monotone system, and we can make use of it for a general case where we have bounded derivative type of system. These two ideas will be presented in a two presentation at the coming World IFAC World Congress. So if I poke the interest of anyone seeing this last two slides, you're more than welcome to come and see the full description of how we can implement this. Yeah, and that's it. From my talk, I have three main ideas that I want to convey. The first is monotonicity structure can help with the interval analysis. Second, we can make use of monotonicity in assumption in several settings, model-based or data-driven. And lastly, several problems can be transformed to the monotone case and make use of all those benefits. And that's it. Thank you for listening, and I'm
Yeah.
open for any questions.
Many thanks, Anas, for your very interesting presentation, and I'm pretty sure that we will have some questions. Who
Thanks.
wants to start?
May I?
Fabian.
Yeah, thank you. Thank you very much for this presentation. If I understood you correctly, at slide 37, it was about monotone embedding. The main idea here is to decompose the system function in a monotone rising part and in a monotone falling part. And from this decomposition, there result two coupled systems. Is that right?
Exactly.
Okay. I I heard about mixed monotone decomposition. So this is, I think, the same idea.
You're exactly correct, but the slight difference is the work established the idea of this mixed monotone embeddings account for the case where you cannot work with for a controller. So here the alternating simulation relation gives a more uh, nice tool to work with, which is I can establish a controller for this abstraction or this embedding and use it to control the original system. But in the previous work with mixed monotonicity, it was done only for verification purposes, not synthesis.
I
And this is
see.
the new things about this embedding. But you're
I
correct.
okay.
The idea comes from there.
First, thanks. And the second point I have is it was about the monotone transformation. I didn't get the point fully. I think it was at slide 17 and the following ones.
This one.
Exactly. And I'm not sure if I understood you correctly here. Does this decomposition in two sets follow the same idea?
Yes, exactly. But one using the upper bound on the derivative and one using the lower bound on the derivative. Here in the scalar case, you see the data set will be transformed as generated from the function h or the function g. So one will be d minus and one will be d plus.
Yeah,
The d
okay.
minus is generated from h and d plus generated from g.
So and then H and G are monotone rising as strict monotone rising and falling functions.
I think both are rising, but yes, if it's decreasing with just a flip, it could be the other way.
Okay, thank you.
Yeah, I would also like to ask a question concerning the slide 37 that you had before. And it's really a nice idea that you're doing this decomposition in order to subsequently do a control design. Now, what can happen in this case, and maybe even quite frequently, that if your original system model A times X, if this is stable, what could happen is that this separation of the rising and falling parts leads to an augmented system model, which then is unstable. And what even further becomes critical then maybe afterwards is if you want to do a control design, maybe even the augmented system model is no longer controllable.
Yes, you're
Yeah.
true.
Do you have any, let's say, except for trying out, do you have any guidelines to a priori detect whether this will be working or not?
So, like, there's some assumptions I didn't add here. First of all, like, it followed a work of George Papas and Antoine Girard, where they established this this simulation function. And for that, first of all, they established that the system is stabilizable. Because the way to establish this interface going from the working with um, from the controller of the embedding system to the concrete needs to use a controller for the original which stabilizes. So there's a hidden assumption. And the other hidden assumption that, yes, that I didn't speak about here, if you want the interval to be meaningful, for sure you need your abstraction to be stabilized. Otherwise, the interval, this mapping will always be correct. The middle point between the lower and upper bound on the interval will always be close to the original system, the concrete, but the interval itself could grow unbounded. So, under the assumption that the abstraction is stabilizable, then yes, we can make use of this. So there's a hidden assumption there.
Yeah, okay, many thanks for this clarification. And then I was wondering, and there's also the idea that Fabian just asked, if you have originally a system model which has an upper bound which is monotonically increasing, lower bound that is decreasing. You did this type of rotation of the map, and then you performed the identification under the assumption of monotonicity. Have you already done some work that allows you to tighten those slopes for the lower and upper bound as soon as you get further measurements? Because what you
Okay.
could do is at runtime, let's assume you have scarce data points. You know a priori bounds for those slopes. I think you call them alpha and beta. And they definitely need to be conservative. And then you're doing, after this transformation, the system identification. Now let's assume you're running the system, you're getting new measurements, a sensor is providing further information, and you could definitely get better as soon as you see new measurements. Then you could firstly tighten the interval boxes that you had shown. And afterwards, what you could do is also tighten alpha and beta.
Exactly correct. You had a really nice idea, and actually we have a paper on that. It's super nice, but like at least for this case where we calculate the over approximation, it's a bit computationally prohibitive to do it online. But what we do, we take your idea and we apply it to a window. So we don't have the least conservative update we can have, but at least it's doable online. So exactly as you said, we have the new data, we tighten the over approximation we have, and it allows us to go and reach new places that we were not able to safely reach before we start the online process. Exactly, we have a paper on that.
Yeah, that's very nice. And then I have a final question. If you're using this, this identification procedure for monotone systems, what you could do is also, as soon as you get further information, you could say, for example, if you refine the model for a subsystem component, which is monotone, which is then further interconnected with another monotone system. And what is then definitely happening after this tightening, the bounds of the output of the system just become tighter. They never will be outside due to the inclusion properties of interval arithmetic. Have you already considered this to put this somehow in a framework for a contract-based system design?
No, but it's a really nice idea.
Yeah. I can forward you an article that has recently been published in AT Automatisierungstechnik,
Okay.
which I did together with one of my co-workers here in Oldenburg. And what we did is a tube-based contraction scheme to derive contracts for dynamic system, for interconnected dynamic systems. And I think in the special case of monotone systems, yeah, your system reformulation, even maybe with the monotone embeddings, could be very helpful for that.
Yeah, I'm looking forward to that. Thanks for the suggestion.
Yeah. Okay, many thanks, Anas. Now let's have a look at the audience. Are there further questions? Doesn't seem to be the case. Then I'm thanking you once again for a very interesting presentation. Also, many thanks for answering all the questions and for the nice discussion.
Thanks.
And yeah, this has now been our last interval seminar before the summer break. Yeah, there will be conferences upcoming, for example, the European Control Conference quite soon. And yeah, I'll announce as soon as I fix the new dates, yeah, the restart of the interval seminar after our summer break. Until then, have a good summer break, enjoy the conferences that you will be attending, and see all of you soon.
Thanks, many thanks. And also, like I should add, but if you I poke your interest in anything, please feel free to contact me and let's have a discussion about it.